All right, today we are going to move into our next unit on momentum and energy. And this lesson is going to introduce the concepts of momentum and something else called impulse. So our objectives are just that: define the momentum of an object and determine the impulse given to an object. And we'll see by the end of this lesson what is the relationship between an object's momentum and something called an impulse. All right, so momentum. Let's look at a couple cases here. If I let this big truck and a skateboarder head down the hill here, let's ask a couple questions about it. First, which one has a greater inertia? Well, we know, right? The measure of inertia is mass. So clearly the truck is going to have greater inertia than the skateboarder. It's going to take more force to get the truck's motion to change than it will be for the skateboarder. But now let's ask the question, what has greater momentum? So we've all heard that term before, right? Momentum. Sometimes we hear it in the context of, wow, this team really has momentum. We've won 3 games in a row, right? So it means we've got some movement in some direction, right? So which of these do you think would have greater momentum? Well, if we watch them go down the hill here together, what would you guess? The truck or the skateboarder? Well, we know the truck has greater inertia, mass, we said that. The truck also has greater momentum if they both travel at the same speed. Now, what happens if we change their relative speeds to the point where the truck is at rest and the skateboarder is the only one that's moving? Now, which has greater momentum? Well, it's hard to think that an object that is at rest has much momentum. So we'd have to say the skateboarder has more momentum than the truck, which is true. Okay, the truck still has greater inertia, but it has 0 momentum. So what is this telling us about the concept of momentum and what determines it? So let's look at our definition. The momentum of an object is equal to the mass of the object times the object's velocity. So it's as simple as that. Multiply the mass in kilograms times the velocity in meters per second. So in order for an object to have momentum, it has to have both mass and velocity. Now, velocity is a vector quantity, mass is not, but velocity is, so momentum also will be. Therefore, it will not only have a magnitude, but a direction. Now, the symbol we use for momentum is m times v, or I'm sorry, p. The symbol we use for momentum is small p, okay? And so if we write the mathematical equation for that, p, or momentum, is equal to mass times velocity. And we don't have a special name for momentum units. It's just simply kilograms for mass times meters per second for velocity. Sometimes we refer to momentum as inertia in motion, okay? So the object has to have both mass and velocity to have momentum. That's the big idea here. All right, let's look at a couple simple examples, see if we can apply the basic math here. So if you have a 60 kilogram halfback running east at 9 meters per second, right? What would be its velocity? I'm sorry, momentum. Let's do the same thing, calculate the momentum for a 1,000 kilogram car moving north at 20 meters per second. Well, we simply have to multiply the mass and the velocity together. So for the part A here, 60 times 9 gives us 540 kilogram meters per second, and we'll include the direction east, same as the velocity. Now let's do the same thing for the momentum of the car. We simply multiply its mass times its velocity. We get 20,000 kilogram meters per second. And because the velocity was north, the momentum is in the north direction. Okay, so simple, just mass times velocity. Now let's look at the relationship here between those 3 variables, momentum, mass, and velocity. So a truck has a momentum of 10,000 kilograms. What would be the new momentum if the velocity of the truck were doubled? Or what if we doubled the mass? We just, while it's moving, we lowered a huge stone or weight into the truck so that it doubled its mass. Well, what if we doubled both the mass and the velocity? What would happen to the momentum? Well, we use our relationship, right? Mass times velocity equals momentum. So if we double the velocity, we're going to double the momentum. So it would go from 10,000 to 20,000. How about if we doubled the mass? Same thing, right? We would go from 10,000 to 20,000. If we double both the mass and the velocity, we now are going to increase it by a factor of 4. So we would have 40,000 kilogram meters per second. Okay, so we would say both mass and velocity are vary directly with the momentum. All right, can we think of a case where the truck and the skateboarder could have the same momentum and neither of them are 0? What would have to happen? Think about that. Well, in order for them to have the same momentum, but very different masses, they would have to have different velocities. Which one would have to have a greater velocity in order for them to have equal momentum? Well, the skateboarder, right? If the skateboarder moves really fast, its mass times velocity could be equal to that of the truck. Okay, so let's look at an example. If we have a 10,000 kilogram truck that's moving at 1 meter per second, what would the speed of a 50 kilogram skateboarder need to be in order to have the same momentum? Well, we can simply just set their two momentums equal to each other, right? So mass of the truck times velocity of the truck has to be equal to the mass of the skateboarder times the mass or velocity of the skateboarder. So if we multiply those together, put in the values where we have them, and then solve for the velocity of the skater, basically it's going to be 10,000, right, divided by 50. So the skateboarder would have to go 200 meters per second. Now it makes sense. If the truck has 200 times more the mass, then the skateboarder would have to have 200 times greater the velocity in order for them to have the same momentum. Now, what actually causes an object to change its momentum? So we're going to start with our relationship again. P, momentum, equals mass times velocity. Now, there's two ways we could change it, right? We can either change the mass of an object or we can change its velocity. But it's not very common in real life that we could kind of instantly change the mass of something, right? We had that example where we lowered a weight into the back of a truck, but that's not typically how an object's momentum is going to change. It's going to change by changing its velocity. So if we wanted to calculate the change in momentum, we would take the mass and multiply it by the change in velocity over time. Now that should look familiar to you, right? Change in velocity over time is equal to the acceleration, right? When we way back at the beginning of the year when we defined acceleration. And so we know from Newton's second law, force is equal to mass times acceleration. Now, we're going to do one more thing to this relationship, this equation, is we're going to multiply both sides by the change in time. So we get it out of the denominator. And now notice we have this expression, force times the time equals mass times the change in velocity. Okay, so force times some time period is going to be equal to the change in momentum, mass times change in velocity. So we're going to call this value on the left side force times a certain amount of time impulse, okay? And that equals the change in momentum. So this is the key concept here in terms of this new property we call impulse. So impulse, think of it as a certain force we apply for a certain amount of time in order to change an object's momentum, okay? All the problems we've done so far with our free body diagrams and Newton's second law, force has just been constant, right? We haven't paid attention to how long the force is applied. It was just simply a constant force there. Now what we're saying is, what if we just apply the force for a certain period of time? That will give us the actual change in momentum. So let's officially define this. It says impulse is the product of force and time interval during which the force acts. So product again just means we multiply. So here's what it looks like. We use capital I as the symbol for impulse. And impulse also will be a vector quantity, right? Because force is a vector quantity. And it's simply equal to force times the time period or change in time. The units are equivalent to momentum, kilogram meters per second. But since we're multiplying force and time, we can simply write the units as Newton times seconds or Newton seconds. Newton is the units for force, and of course, seconds is the unit for time. So impulse is also equal to the change in momentum, right? So we could calculate impulse a different way by simply multiplying the mass times the change in velocity. So we really have two different ways in which we can calculate impulse, right? Either force times time or mass times the change in velocity. And they will both give us an equivalent impulse. So think of an impulse as the force that's being applied, right, to an object over a certain period of time. All right, so that description here in the yellow box pretty much sums up this big concept. Force applied over time results in a change in the object's momentum. All right, let's look at some examples. We want to calculate the impulse for a 60 kilogram halfback that experiences a force of 100 newtons for 3 seconds. And part B, a 0.2 kilogram tennis ball that experiences a force of 500 that changes its velocity by 40 meters per second. Now, at the top of the screen here, you notice I put in our two ways to calculate impulse: force times the change in time, or mass times the change in velocity. So let's look at each of these problems and figure out which way can we calculate the impulse, right? Which values do we have available to us? So for the first one, we don't know the change in velocity, but we do know the force and the time period. So we can simply multiply those together and we would have an impulse of 300 Newton seconds. In the second example, right, we don't know the time period, but we do know the mass and the change in velocity. So we can simply multiply 0.2 kilograms times 40 meters per second, and we get an impulse of 8 kilogram meters per second. Now, impulse can have either units here, Newton seconds or kilogram meters per second. It just depends on which way we calculated it, right? Force and time versus mass and change in velocity. Now, once we know the impulse, could we calculate the change in velocity for the football player? Well, sure, right? Or could we do the same thing now for part B? Now that we know the impulse, could we find the time that the force is applied? So let's do that, right? Our total impulse, 300 Newton seconds, has got to be equal to the mass times the change in velocity. So we just need to divide by 60, and we would get a change in velocity of 5 meters per second. Okay, so applying that force of 100 newtons for 3 seconds will change the football player's velocity by 5 meters per second. If we're applying the force in the same direction, then it's going to accelerate. If we apply that force for 3 seconds in the opposite direction, it's going to decelerate or slow down our football player. How about the bottom here? Well, take our impulse and set it equal to the force times the time. So if we divide by 500, we see we actually get a very small time period. Probably what we're doing is we're hitting this tennis ball with a tennis racket. And you know that the tennis ball and the racket are in contact with each other for just a very short amount of time. So very high force over a short amount of time. So this is what, 16 thousandths of a second that we're applying that force of 500 newtons. All right, let's look at a couple other cases, right? To increase an object's momentum, we want to apply the greatest force for as long as possible. Okay, that makes sense, right? Because that's the first way we calculate or determine impulse, force times time. So the larger the force for the longest period of time, we will result in the greatest change in the object's momentum. So for example, if we hit a baseball with a bat, any great batters, if you watch them, right, they follow through with that baseball bat, right? They don't just swing halfway till they make contact with the ball and then stop the bat at that point. They swing all the way through. Why are they doing that? Well, If you've played baseball, you know follow through with the bat is important because you can maintain contact between the bat and ball for a longer period of time. You can apply a greater force for a longer period of time, and therefore a greater change in the ball's momentum, greater impulse. Now, most of the problems we're going to do, we're going to assume that the force over that time period is an average force, right? In reality, we know the force is going to change between when you first make contact with that baseball until you follow it all the way through. But for the problems that we're going to do, we'll assume that the force is constant, or we have an average force over that time that it's in contact with the object. Now let's look at a second case here. What if we want to decrease momentum? Well, we have two ways to do it, right? If we've got two cars, one's going to run into a brick wall and the other's going to run into a haystack, right? Which one would you prefer to use to stop your car if you lost your brakes? Now, I think we would all agree that hitting a brick wall with a car is not going to have a very good outcome. Whereas driving our car through a pile of straw or hay is going to be a much better way to bring the car to a stop. But why is that, right? What's the physics behind that? Well, think of it this way. Remember, impulse is equal to force times the time. So when we stop against the brick wall, we have a very large force for this very small time period, right? The impulse to stop either car is the same since they both have the same speed and mass. But when we hit the brick wall, we're going to experience a very large force for a short period of time. Now it's that very large force, right, that is going to hurt us, that's going to kill us. So here's a way we could represent that, right? Big force, small period of time. Now, when we hit the straw applies a smaller force over a longer period of time, right? So small f and big T. And remember, it's the force that does the damage, right? When you're in an automobile accident, it's the forces that the car and your body experience that does the damage. So any way we can bring you or the car to rest with a smaller force over a longer period of time is going to have much less of an impact, much less dangerous, much less damage done to you or your car. So let's look at some examples of that, right? We've got a vehicle that's traveling at 26 meters per second and a mass of 2,200 kilograms. And we're going to stop it three ways, right? We can gently put on the brakes over a period of 21 seconds, or we can slam on our brakes and bring us to a stop in 3.8 seconds, or we can hit that brick wall that we saw in the previous example here, right? And that will stop us in less than a second. So can we calculate what the average force exerted would be in each of these stops, right? How much difference would we see in the forces? So remember, we've got these equations, right? Force times the time equals the change in momentum. So the change in momentum will be the same for this car in all three cases, right? Because we've got to go from 26 meters per second to 0 when it comes to a stop, and we're multiplying that by the same mass. So if we calculate this, right, we'd have 26 meters per second times 2,200, and then divide that by 21, we would see we would get a force of about 2,700 newtons acting on the car from the brakes. If we slam our brakes on, notice how much greater that force becomes. Right? Shorter time, larger force. So a negative 15,000 newtons. And then if we hit the brick wall, look at the force, 260,000 newtons being applied for just a fraction of a second. That's where the damage occurs, right? There's not very many human bodies or even cars for that matter that can survive that large of a force. All right, so that's what we are covering for today, momentum and impulse. We've learned how to define and calculate momentum, simply mass times velocity. And we've learned to determine the impulse given to an object. And the impulse, member, is what is used to change the object's momentum. And we can calculate it two ways, mass times the change in velocity, or the force and how long a time period do we apply that force. Okay, that's it. Thanks for your time. There'll be a lesson posted in Classroom.